Now this is precisely what what we were seeing earlier. Remember, there was a figure. Okay, there's the figure here. Okay, so you have a series of delta functions. You have a continuous time signal xc of t. When you multiply it, what is left is only the Dirac deltas are left. Everywhere else the function has gone to 0. But the Dirac deltas are now scaled by the corresponding value. So for example, these are the scaling values of the Dirac delta. Okay, you have the scaling value here, like this you have the scaling values. So this is what we are now trying to capture in our representation. Okay, so I hope you are comfortable with that, and we are able to write down this expression. Now, when we multiply two signals in the time domain, it is the convolution in the frequency domain. So, xc of t multiplied by s of t, this is multiplication. When I look at it in the Fourier transform relationship, what we get here is 1 over 2 pi xc of j omega convolved with the Fourier transform of s of j omega. Okay, the signal is band limited, so it's minus omega n to omega n. So we know what xc of j omega is. So this is known. This is known. We must evaluate this one. We must evaluate. Okay, so let us do the evaluation of that. So how do we do that? So take a look at s of t. S of t is summation n equal to minus infinity to infinity delta of t minus nts. Okay, first question, is it a periodic signal? Periodic signal, the answer is yes, because you see that these delta functions are coming in a period. And the second question is, what is the period? And the period happens to be equal to Ts. Now, if you have any periodic signal, you can do the Fourier series representation. So, what does Fourier series representation say? That means this periodic signal s of t can be written as a sum of signals. So, we can say m equal to minus infinity to infinity a subscript m, Fourier series coefficient, and it is a complex exponential. So, e power j 2 pi by Ts, that is your fundamental frequency, times m times t. So, basically you are writing the Fourier series representation of this particular signal. Okay, and you can go ahead and write down the expression for am. The Fourier series coefficient is 1 by the period minus Ts by 2 to Ts by 2. Delta of t is your the function that occurs in one period, e power minus j 2 pi by Ts nt times dt. Okay. I hope you are familiar with the how we compute Fourier coefficients. So basically write down the expression for this, and also please carry out the delta of t means it will be non-zero only at the value t equal to 0. So this basically this integral will collapse, and what you will get is that each of these coefficients is equal to 1 over Ts for all values of m. Okay. So s of t can also be written, so this Dirac delta sequence can also be written as 1 over Ts summation m equal to minus infinity to infinity e power j 2 pi by Ts times m times t. Okay, this is an alternate expression for s of t. Now you may wonder, why are we doing that? Because we have a result from continuous time Fourier transform which we will use. So let us copy this to the next page and look at what is the form that we can get. Okay, so this is the expression that we have, and we know that there is a Fourier transform relationship which says the complex exponential e power j omega naught t has got a Fourier transform relationship which is given by a Dirac delta, but in the frequency domain. 2 pi times a Dirac delta which is located at omega equal to omega naught. Okay, so this is the Fourier transform relationship. So from here we can then say, using the result that we have, so if you are saying this one, so using result 1, we can say that the Fourier transform of S of t, which is given by S of j omega, can be written in the following form. You get a scale factor of 2 pi from the Fourier transform, 1 over Ts is a scale factor from the signal, and you will then have m equal to minus infinity to infinity delta of omega minus m omega naught. Okay. So this is a very important relationship for us. So if the signals are appearing with actually not omega naught, it's omega s, it should be the omega s. Okay. Okay, so in our case it will come out to be multiples of omegas. The illustration that we used, so this will be m omega s. Okay, so this is because it's related to Ts. So what we are saying is the Fourier transform of S of t is a Dirac deltas, a sequence of Dirac deltas which are spaced at this particular rate. Okay. Notice that the height is 2 pi by t, so all of them are 2 pi by t, and the spacing is omega s. You have 0, omega s, 2 omega s, and so this is the spacing between these is omega s. So the two functions that we are going to convolve are xc of j omega convolved with s of j omega. Okay, and s of j omega, so this is the same as xc of j omega convolved with 2 pi by Ts, summation m equal to minus infinity to infinity delta of omega minus m omega s. So basically you are going to convolve the first function, the triangular function, with these delta functions. Okay. So also there is a scale factor of 1 over 2 pi in the Fourier transform. So this 2 pi and 2 pi will cancel, leaving us a scale factor of 1 over Ts. Now whenever you convolve xc of j omega with a delta function, you will get the original xc of omega. However, if the delta function is shifted in frequency, you will get the corresponding shift in the spectrum also. So what you will get is 1 over Ts summation m equal to minus infinity to infinity xc of j times omega minus m omega s is what you will get. Basically xc of j omega convolved with each of the delta functions will produce for you. So this convolved with this will produce for us the equation, that the figure that is present here. So this is what is the Fourier transform of the sampled signal xs of j omega. Okay. I hope you are able to visualize this, maybe take a minute to go through the steps. What we said was we are multiplying the two signals. Okay, we are multiplying the two signals. where is that? Okay, we are multiplying xc of t and s of t. Xc has got a Fourier transform which is xc of j omega. So basically this is the representation, this is the signal and its Fourier transform. Now s of t has got a representation which is given by s of j omega. So this is the Fourier transform of s of t. So when you multiply s of t and x of t, you must convolve xc of j omega and s of j omega, and that is what we get as the expression that we have here. Now I need you to note the following important aspects of it. Okay, the first one is a scale factor. There is a scale factor. The second one, the spectrum of the continuous time signal xc of t was a band limited signal from minus omega n to omega n. But once you multiplied it with the impulse train, notice that you get now many copies, many copies. So this basically tells you that there is a repetition of the spectrum. Not only is there a scale factor, there is a repetition of the spectrum. What was originally only one portion of the signal, now that signal seems to be replicating, and how many times? Infinite number of times. So replication of the spectrum, that is the second aspect that I want you to keep in mind. And the third aspect is these copies of the spectrum are shifted by multiples. So these are the shifts. Okay, and the shift is multiples of omega s. Multiples of omega s. So if I were to ask you to describe for me the spectrum of the sampled signal xs of t, which is the product of the impulse train and the continuous time signal, remember this is a mathematical framework. So the spectrum will be a scale factor 1 over Ts, then infinite number of repetitions of the spectrum with each copy shifted by multiples of omega s. Okay, so I hope you are able to understand, and this equation is exactly what we have here. Notice that we have the scale factor of 1 over Ts. You have the signals all at different shifts of omega s, and there are infinite number of them which are present from start to end. Okay, I hope you are comfortable with this particular representation, because this is going to give us some very important results. Okay, the first thing, let me call that as result number 1. Result number 1. Okay, the first copy, okay, or the original signal. The original signal is at omega equal to 0. That's the original signal. Okay, let's highlight it in red. Okay, the first copy corresponding to m equal to 1. The first copy corresponding to m equal to 1, this occurs at omega equal to omega s. Okay, the first copy, maybe don't have to say first copy, copy at omega m equal to 1. So and then you have another copy at m equal to minus 1. That corresponds to the center frequency is omega equal to minus omega s. Okay, so this is m equal to minus 1. So you can you can look at how these things are occurring, and correspondingly you look at this and understand this. Okay, now what is the frequency range of the original signal? It goes from minus omega n to omega n. Am I right? That is what we have. Now the first copy is centered around omega s, the highest frequency component will be omega s plus omega n, that will be the highest the positive frequency, and the other end the frequency will be omega s minus omega n. I hope you are able to see that. So, basically the spectrum copy is from minus omega n to omega n, but if the center frequency has moved to omega s, then what you will get is omega s plus omega n as the positive frequency, omega s minus omega n as the other frequency. Now, if we do not want these copies to overlap in frequency, okay, we do not want these copies to overlap. So, if we do not want copies to overlap, okay, if you take it only for the first one between m equal to 0 and m equal to 1, okay, at m equal to 0 comma m equal to 1, what will that condition be? The highest frequency component for omega naught is for the center m equal to 0 is omega n, right, and the lowest frequency component of m equal to 1 is omega s minus omega n, correct, omega s minus omega n. So, you can see that that's what is highlighted here. So, we have omega n as the highest frequency component, omega s minus omega n as the lowest frequency component of the first copy. Now, this must be less than this quantity. Do you see? If this condition is satisfied, then you will not have overlap of signals. Okay. You can even allow the equal sign. It can touch each other. The highest frequency component of the m equal to 0 copy and the lowest frequency component of m equal to 1 can touch each other. This is the condition. Okay. So, what does this tell us? 2 times omega n, you bring omega n to this side, must be less than or equal to omega s. Or in other words, omega s greater than or equal to 2 times omega n. Do you recognize what this result is? This is the Nyquist theorem. The Nyquist theorem told us that you should do at least twice the highest frequency component. And why did it tell that? Where did it come from? It comes from this particular mathematical framework, because when you have sampling, you will introduce copies of the original signal. And if you do not want the copies to overlap with each other, then this condition is going to give you the required, will give you the property that will ensure that there will not be any overlap of the copies of the signal. On the other hand, if you do not satisfy, so this is a case where Nyquist theorem is satisfied. Nyquist theorem is satisfied in this particular case. Okay. Now, in the case where Nyquist not satisfied, then what happens? The copies of the signal occur closer to each other, the copies overlap and cause distortion to the original signal. The original signal is what we see at the top. Okay. Now, the important step here is we have fully understood what is the sampling process, what is the Nyquist criterion, why these copies come about, how do we make sure that the copies don't cause interference to each other. We will also be able to answer another very important question. Now, if I want to get back my original signal, remember we said sampling takes you from continuous time to discrete time, and then reconstruction, basically the process that goes from discrete time to continuous time. What is that process? That process can also be very nicely described here. Is if you now apply an ideal low pass filter which will keep the original copy m equal to 0 and remove all other copies. Okay, all other copies eliminated, m equal to +1, -1, m +2, -2, everything. then what you will get is the signal that is remaining will be only the spectrum that corresponds to the first one. So, this is my reconstruction filter. Reconstruction filter is the one that produces for me my original signal back. How can I do that? By passing it through a low pass filter and removing all the unwanted copies. And the important thing to note is that this is possible only if you have satisfied Nyquist criterion. Because if you have not satisfied Nyquist criterion, notice in this case I can apply a low pass filter, but what comes out of the low pass filter will not look like the original signal. It's a distorted version. In fact, this distortion that you have when you do not satisfy Nyquist is called aliasing distortion. Okay, this is called aliasing distortion. Okay, very important results that we have covered in today's class, and let me sort of summarize it for you. Now, we started off by saying that we would look at a train of Dirac deltas. We said that it is a periodic signal, so we can write down the Fourier series representation. So, what we have written down here is the Fourier series representation of the periodic signal. Fourier series representation. Now, the advantage of this is that we have a representation in terms of the Fourier transform of these complex exponentials. So, that enabled us to get a Fourier transform of the Dirac delta functions, Dirac train. It turns out that the Dirac train in the time domain is also a Dirac train in the frequency domain, but with different spacing, with spacing of omega s and the scale factor of 2 pi. Now, we then went back to the original expression and said, if I want to multiply in the time domain xc of t and s of t, that is the same as convolving the two spectra in the frequency domain, and what we get as the Fourier transform of the sampled signal xs of j omega is a signal where you get an infinite number of copies of the original spectrum. These copies are scaled by a factor 1 over ts, and the copies are all centered around multiples of omega s. If omega s satisfies Nyquist criterion, then there will not be any overlap of these copies. And if you have satisfied the Nyquist criterion, then we can apply an ideal low pass filter and we can remove the copies of the unwanted copies to get the original reconstruction. So, I would like to stop at this point because this is an important concept that we have developed. What is the process of sampling? What is the representation? What is the mathematical framework? How do we look at the spectrum of the signal after sampling has occurred? And then what is the condition that we need to satisfy so that there will not be any aliasing or there will not be any distortion caused by the overlap of the copies of the spectrum, and that then also tells us what is the ideal reconstruction filter. So, these are important concepts. I want you to not only have a good understanding of the sampling process and how to choose the sampling frequency, also look at the mathematical framework and also be able to appreciate what we have discussed in today's class. So, what we will see in the subsequent lectures is to look at what is the process of reconstruction. Remember, we said that the process of reconstruction is the pink ideal low pass filter. We would like to look at what is the ideal reconstruction filter, how do we get the continuous time signal back from the discrete time. So, today's class we have been able to go from continuous time to discrete time. We have at least in principle showed what are the requirements for us to satisfy the Nyquist criterion, and we have looked at several examples where we have taken a signal, looked at its Fourier transform and said what is the highest frequency component, and based on that we have specified what is the Nyquist sampling frequency required. So these are important concepts. I would like you to review these concepts in a thorough manner so that then we are ready for the next session, where we would look at the reconstruction process. We would look at a little bit more details, more in detail about the sampling process itself and some of the new insights that we can get from that. Okay, we will stop here. Thank you.